All right, we've been talking about molarity, and molarity is a great way to measure the concentration of a solution if you have a liquid, because it's really easy to measure the volume of a liquid. You just take a graduated cylinder or something like that, and you dump the liquid in there. But what about non-liquid solutions? Can we still measure the concentration of non-liquid solutions? And when I mention non-liquid solutions, remember we think of something like if I had a sample of that something, and everywhere in that something you could find a mixture of items that are dispersed evenly, right? So everywhere inside this square, we're going to have a mixture of blue and black dots. So what's something that is a solution that's around all of us? Oops, sorry, my photo keeps going away there. What's something that's a mixture around all of us? Well, air is a mixture. And it is, by the way, just to throw this word in here, a mixture of things where every particle is mixed evenly is called homogeneous, or homogeneous. Homogeneous. Oops, I misspelled it. Oh well. Homogeneous. Not really important that you know that, but air is a homogeneous mixture. Most air, depending on where you are in the United States, is about 78% nitrogen. It's actually N2. So most everywhere it's about 20% oxygen. And then, we can have, there's about 2% in there, and that other 2% is usually mostly water, and you get some CO2 in there. And then there's some other trace gases, things like argon. You got a lot of argon. There's xenon in the air. There's helium in the air. There's if you're really unfortunate, there might be some radon in the air. Ooh, bad for you. So air is something we can measure percentage-wise. There's another unit we can use to measure that, but we'll talk about percentages in a couple of days when we talk about percent composition of solutions. But solids are even more fun to me because one of the solids that we talk about is jewelry gold. Jewelry gold. If you've got a piece of jewelry, you can take it off and you can take a look at it. Keep my wedding ring on me at all times. Let's hope it doesn't go flying off somewhere. But usually if you've got like a ring, you can look on the inside, and there's often printings on the inside. Mine's nice and beat up because I wear it all the time. And on the inside, for those of you not familiar with it, gold is always marked in carats. So gold, jewelry gold especially, is measured in carats, and that's carats with a K. Carats with a K, and it's abbreviated capital K. All right. Jewelry gold is marked by carats because that tells you how pure the gold is. So concentration for jewelry gold is measured in these carats. It's also purity, right? So purity becomes concentration is something we talk about in chemistry. Purity is something you talk about as a jeweler. And pure gold is set at 24 carats. So have you ever heard of 24 karat gold? That's pure gold. Now, pure gold is very soft, very easy to bend, right? If I had a ring like this on and I was like trying to squeeze it on my finger, it would actually bend and shape around my finger. So most jewelry can't be made out of pure gold. If you had a necklace, right, the weight of the necklace would be enough to snap the links of the chain around your neck. So we can't make jewelry gold out of pure gold. What we do instead is we say pure gold is 24 carats. So, for example, if I have 16 karat gold, which is what this is, 16 karat gold means that I have 16 parts gold and 8 parts something else. Now, the something else can change the properties of the gold. This is white gold. Most white gold usually has nickel in it, or if it's a little more expensive, they can use silver. And often they'll add zinc in there because zinc kind of helps strengthen the gold. But it turns it this whitish color. Yellow gold often has mostly copper added to it. If you add a lot of copper, it becomes this red gold kind of thing. If you mix in, what's really weird is nowadays you're starting to get this gray gold that's got palladium mixed into it. You can see sometimes if you want to get like an orangish gold, they'll do like kind of a copper-silver mix, and it's kind of really neat. But yeah, what parts we put in here changes the color and also changes the density of it, changes the strength of the gold. So that's kind of neat. What we do is we're going to take that and we are going to talk about, in chemistry, instead of talking about carats, we use a unit known as molality. I know it sounds a lot like molarity. What makes it even worse is molality is abbreviated with a little m. It's a lowercase m. Molality, lowercase m. Molality, because it's often used with solids. We are tomorrow going to apply it to liquid solutions as well, because there's a really neat thing you can do with it then. But a molal, right? Molality, molal. A molal is a mole of solute per kilogram of solvent. So this becomes something really easy for us to be able to measure of a solid, right? In particularly if you're planning out gold and you want to figure out how much gold you're going to make. If I want to make 16 karat gold, what I can do is we can take if I take 8 grams of copper and I melt that down and I dissolve it, that is, I add it to 16 grams of gold, right? So if I take 8 grams of copper dissolved in 16 grams of gold, I've made 16 karat gold. It'll probably be a nice yellow color. But that's how you make 24 carats, right? 8 plus 16 gives me 24. So we have 16 parts gold, 8 parts copper. What would be the molality of this solution is a question that we would ask as chemists. Excuse me. So what are we going to do? Do this problem just like we do the molarity problems. We're going to draw a straight line right here, equals. Out at the end, it's asking me what is the molality. So here's where things get a little different from molarity. Instead of molarity, we have moles per liter. In molality, we're going to do moles of solute per kilograms of solvent. And the reason we're going to do that is because it's often easier in molality problems to figure out solute and solvent. Remember, the solute gets dissolved in the solvent. So we're going to look for things in the problem when we read this problem. Grams of copper dissolved in, so copper gets dissolved into the gold, right? So that makes this the solute, and that makes this the solvent, because the solute goes into the solvent, all right? So when we put these things out here in our problem, the solute part goes on top, the solvent part goes on bottom. So we're going to put 8 grams of copper, because that's our solute, and on the bottom we're going to put 16 grams of gold, of AU. All right? So now what we're going to get is we are going to get 2 problems that we need to work out. There's going to be 2 steps here. We need to convert grams of copper into moles, and we need to convert grams of gold into kilograms. Does not matter which one you start with. I usually like to start with the bottom one. I usually like to start with grams to kilograms because I think it's the easiest. So I'm going to do, in the next step, I'm going to take grams of gold up to the top, and I'm going to convert that into kilograms. To do that, I have to go way back when we talk about grams and kilograms, and I have to know 1,000 grams equals 1 kilogram. So because 1,000 grams is equal to 1 kilogram, I can put those numbers into this equality. 1 goes in front of the prefix. Scientific notation goes in front of the base unit. Oh my goodness, remember that? And by the way, back in the day when we wrote this, instead of writing 1,000, we'd write 10 to the third. Not really important to remember all that, to go back and review all that. We're just going to memorize the fact that 1,000 grams equals 1 kilogram. All right. What cancels out? Grams AU, gone, gone. And we're only left with kilograms on the bottom, which is what we want. All right, next step is I got copper, 8 grams of copper. So we're going to put grams copper on the bottom. Can I go from grams to moles? You better believe it. You better be able to do this. We've been doing this for weeks. What goes in front of mole? A 1. What goes in front of grams? 63.55. A number I just randomly made up. No, I didn't make up this number. I went to my trusty, dusty periodictable.com, ptable.com. I'm not sure why it freaked out on me there for a minute, but there we go. And I go to copper, and you see copper is 63.55. You got to round, right? All right. Oops, that is the wrong problem. There we go. Back to this problem. There we go. All right, so grams of copper on top, gone, and on bottom, gone. And we are only left with moles on top. So we got moles on top, kilograms on the bottom. So I'm going to plug this into my calculator. It goes 8 times 1,000 times 1. I'm not going to do that. Divide by 16. Divide by 63.55. And when I plug that into my calculator, whoop, I'm going to get 8 times 1,000 divided by 16 divided by 63.55. I get 7.87. Now I would like for you to try the reverse. What is the molarity of 16 grams gold dissolved? I'll write it out. Dissolved in 8 grams of copper. Pause the video, draw your line, do all that kind of work, and let's see what you get. So you get this far and you start looking at that problem and you realize, wait a minute. Gold is now my solute. Copper is now my solvent. If you didn't do that, right, gold's going to go on top. Copper's going to go on the bottom. You need to fix that now. All right, now when I do this, I'm still going to do the first step. Uh-oh. There we go. There we go. All right, I'm still going to do the first step. I'm still going to go from grams. I need to go from grams to kilograms. I need kilograms on the bottom. 1 kilogram is 1,000 grams. Gone, gone. Then the next step, I'm going to go from grams of gold to moles of gold. 1 mole of gold is 196.97, according to my table. 97 grams. Gone, gone. Plug it into your calculator and I got 10.15 molal, all right, which is kind of fun. So if you do it the other way around, you get a very different answer. And that's what we expect. As chemists, that's what we expect. What's really neat here is to do this calculation for multiple. And what most people agree on is by about the time where you get more molals of copper dissolved in gold, that you're no longer dissolving the copper into the gold, right? You're dissolving the gold in the copper, and you're looking at, so somewhere around 10 to 12 carats. Some jewelers will say 12 carats is still gold. Other jewelers will say, nah, 10 carats is still gold. But really, if you buy 10 karat gold, it's actually some other metal. It's mostly some other metal, which is kind of fun. Some jewelers get around that by making 10 karat gold, but it'll be 10 parts gold and then like 6 parts copper and 6 parts zinc, or 6 parts copper and 8 parts zinc, excuse me, to make 24. And they'll say, well, you still got 10 parts of gold. It's still the most. But really, it's mostly those other things, which is kind of fun. So anyways, that's molality. You've got a bunch of problems to work on. Go ahead and get started on that.